All right, let's dive into the world of quantum tech. Well, a specific corner of it anyway. We're talking excited states today.
Excited states, always a fun topic.
And our guide is this FAQ article, Anregungszustand in der Quantentechnologie erklärt by Jorgo Schneppert.
Ah, yes, Schmippat.
It means excited state in quantum technology explained, for those who don't speak German. Luckily, Schneppert keeps things pretty straightforward, perfect for our deep dive.
Yeah.
But before we get lost in the science, let's answer the basic question. What even an excited state?
It's one of those terms, yeah, everyone throws around.
But might not actually get.
Right, think of it like a video game.
Yeah.
Your character, they have their normal energy level, right?
Their baseline.
Exactly, their ground state. But then they get a power-up. Suddenly they're in an excited state, more energy, ready for action.
Okay, I like that. So how does that video game analogy translate to, like, actual atoms?
So, Schneppert, he defines it this way. An atom, or, any quantum object, it's in an excited state when it's got more energy than its most stable state, which is that ground state we were talking about.
So it's powered up.
Right. But it can't stay that way forever. It wants to go back to its chill ground state eventually.
Kind of like how no one stays hyped up on caffeine 24/7. There's got to be a come down.
Exactly. And these excited states, they might be temporary, but don't underestimate them.
Right, right. Why should we care about these fleeting excited states?
Because they're not just fleeting. They're, like, essential to some seriously cool tech. Lasers.
Lasers.
Quantum computers, even the stuff that keeps our online info secure.
Hold on. Are you saying the lasers that scan my groceries at the store? Those are using excited atoms.
Yep. Imagine a bunch of atoms all in this laser medium, right?
Yeah.
You pump them up with energy, force them into that excited state.
Like giving them a jolt of espresso?
Yeah, kinda. And
Yeah.
then, as they inevitably chill back down to their ground state, that energy they had,
It's got to go somewhere.
it gets released as light. And not just any light, that focused beam we know as a laser. Schneppert goes into detail about it in his article.
Wow, that's way cooler than I ever thought grocery store lasers were. What about quantum computers? Where do excited states fit in there?
So quantum computers, they use these things called qubits.
Qubits.
Think of them like the quantum version of bits, the ones in your regular computer. And to get those qubits to, do their quantum
I
stuff.
got to manipulate them somehow.
Exactly. And guess how we do that? By putting them into excited states. This is where things get interesting.
Okay, I'm intrigued. Tell me more.
Because by getting those qubits into those excited states,
You can get them too.
to perform calculations way beyond what your laptop could ever dream of.
So we're basically poking these tiny particles with energy, sending them into higher states, and using that to do, like, crazy complex calculations.
Very much. It's like a subatomic dance of energy. And that's what gives quantum computing its power. Schneppert even uses that analogy, the dance, in his article.
Okay, that's wild. But secure communications, how does that tie into excited states? Schneppert mentioned something about quantum cryptography, right?
Right. And this is where the sensitivity of excited states comes in. Imagine you're sending a super secret message and someone tries to sneak a peek.
Eavesdropping.
Exactly. Well, when they do that, they inevitably mess with the excited state of the particles carrying that message.
It's too delicate.
And that disturbance, it sets off an alarm bell, letting both the sender and the receiver know something's up, like a built-in security system.
Whoa. So it's like the very act of trying to spy on the message.
Ruins it.
Exactly.
Yeah.
Genius.
Yeah.
But how do scientists even work with something so tiny and delicate? How do they get an atom or a qubit all riled up into an excited state in the first place?
Well, there are a few ways. One common one is using photons,
Photons.
those little packets of light. They deliver this precise energy boost to the atom, or qubit, like a tiny nudge to push it up to a higher level.
So you're telling me shining a light on something can actually change its energy state at the, like, quantum level?
It can. It's pretty mind-blowing.
It really is. Are photons the only way to do it?
Nope. Scientists also use heat or even precisely tuned electric fields to give those quantum particles the energy boost they need.
So it's all about manipulating energy, getting things to absorb it, release it, carefully controlling those transitions.
Exactly.
But this all sounds incredibly intricate. Are there any downsides to working with these excited states? There's got to be some challenges, right?
Of course. Schneppat actually, he talks about this a bit. One of the biggest hurdles is how sensitive these excited states are.
We've talked about that a bit, yeah.
Even the smallest changes in temperature or stray electromagnetic fields can throw them off completely.
Like a house of cards in a windstorm.
A good analogy. And then there's the fact that some excited states are incredibly short-lived, like we're talking nanoseconds.
In nanoseconds.
Imagine trying to build a computer that runs on signals that disappear that quickly.
That sounds impossible.
It's definitely a challenge, but the potential of these excited states is so huge. Scientists are constantly pushing the boundaries, developing new techniques, new materials to overcome those challenges. And that's actually what we'll dive into in the next part of our deep dive. So we were talking about those challenges, right? Working with excited states.
Yeah, it's like they're so sensitive to everything.
It's true. Schneppat, he really emphasizes that temperature, stray fields, anything can mess them up.
And then some of them just don't last very long at all.
Right, those super short-lived ones, nanoseconds, like poof, gone.
How do you even build anything useful with a signal that disappears that fast?
Well, that's what scientists are trying to figure out. One approach Schneppat mentions is developing new materials. Yeah,
Materials.
materials that are like inherently less sensitive. Imagine creating a container for those excited states, something to protect them from all that noise.
So instead of controlling the whole environment perfectly, you're giving the excited states a little safe haven.
Exactly, like building a fortress to protect a tiny flame. Keep it burning bright no matter what's going on outside.
Okay, so material science is important here. What about those super short-lived states, though? Any way to make them last longer?
That's the big question, isn't it? Schneppat actually hints at some pretty cutting-edge research on that. Imagine being able to slow down time for these quantum events.
Slow down time. That sounds like something out of a movie.
I know, right? But think about if we could stretch out those nanoseconds, even a little.
We'd have so much more time to work with them.
Exactly. It would be revolutionary. Like, instead of a light switch that flickers on and off in an instant.
You could have one that stays on as long as you need it.
And Schneppat, he points to some ways researchers are trying to do this, like using lasers to manipulate the energy levels of atoms.
Lasers. To fine-tune the excited states.
Yeah, it's like using a laser as a tiny wrench, making those energy levels just right to keep the state stable. And it's not just lasers. Magnetic fields, electric pulses.
Even specially designed materials.
Right, a whole toolkit for tweaking these delicate states.
So where's all this leading? What are the biggest impacts we might see from this research? Quantum computers, I'm guessing.
Definitely. Schneppat, he talks about creating qubits, those quantum bits, with much longer-lasting excited states. Imagine a quantum computer where the qubits can hold on to information for minutes, hours, even days.
That would be incredible. We could solve problems we can't even dream of right now.
Exactly. Drug discovery, material science, AI, the possibilities are huge. And Schneppat also mentions quantum sensors.
Quantum sensors, I've heard the term, but
Think of them as the ultimate detectives. They use the sensitivity of quantum systems, like those excited states, to detect tiny changes in their environment, stuff our normal sensors would totally miss.
like a sensor that could detect a single molecule of something.
Or tiny variations in magnetic fields. Think about it, medical diagnostics, environmental monitoring. Schneppat even talks about studying gravitational waves with them.
Wow. Okay, this is getting mind-blowing again. It's amazing to think about what we might be able to do with this technology.
It really is an exciting time. But before we get too lost in the future,
Right.
we should take a minute to appreciate the scientists doing this work. They're the ones exploring this quantum world, uncovering these secrets, one excited state at a time.
Absolutely.
Mm.
Their dedication is what's making all this progress possible. But as we keep going deeper into this quantum world,
Yeah.
we need to think about the bigger picture too, right? The implications, the benefits, and the potential risks.
You're right. Schneppat brings this up too. It's not just about the cool science, it's about using this technology wisely and responsibly. And that's something we'll talk more about in the last part of our deep dive.
So we've explored the how, the what of excited states, but where does this all lead? What's the big picture here with this whole quantum revolution?
Well, that's what Schneppat wants us to think about, right? He doesn't just leave us with science is neat. He wants us to consider the ripple effects of all this excited state research.
I like that. Ripple effects. It's not just about cool gadgets, but how those gadgets powered by quantum stuff could actually change the world.
Exactly. And Schneepat reminds us every big tech leap, it comes with new ethical stuff to think about, societal stuff. And quantum tech, it's going to shake things up big time, so no exception.
So let's talk about those ripple effects. What are some of the concerns that pop up when we talk about messing with these excited states? What does Snepat point to?
One thing he brings up is jobs. Quantum computers, the more powerful they get.
They could start doing things humans do now.
Exactly. Which means, changes in the workforce, job displacement.
That's happened before, right, with new
Yeah.
tech. But it's not just about losing jobs. It's about getting ready for the new ones that'll pop up.
Right. We got to anticipate those changes.
hmm
Education, retraining. That's going to be key.
Okay, so jobs. What else? Anything else we should be keeping in mind as we go deeper into this quantum stuff?
Well, Schneepa also mentions misuse. The same quantum algorithms that could revolutionize medicine, they could also be used for, well, not so good things.
A reminder that power, any kind of power, it can be used in different ways.
Yeah.
Not always good ones.
Right. So international cooperation, responsible governance, those things are going to be super important to make sure this tech gets used ethically.
We need to have those conversations now
Yeah.
before things go sideways. Schneefat's article, it's a good place to start thinking through these issues.
It is. It really pushes us to look beyond just the science. It's like he's saying, okay, we've opened up this quantum toolbox. Now let's figure out how to use those tools wisely.
Exactly. Well, this has been an eye-opening deep dive, that's for sure. Schneefat's insights, they've given us a lot to think about.
Definitely. From the basics of excited states to how they could change everything from computers to communication to sensors.
And beyond the tech itself, just the broader implications of all this for society, for the future.
Yeah, it's a reminder that science, it's not just about facts and figures. It's about understanding our place in the universe and using that knowledge to make things better. For everyone.
Well said. And with that, we encourage everyone to keep exploring the world of quantum technology. Who knows what's coming next? All thanks to these tiny but powerful excited states. Thanks for joining us on this deep dive.